Hello students, I am Dr. Shilpa K. Gowda, Associate Professor, Department of History, SJBIT. Today I am going to explain the topics integrated circuits, operational amplifiers. So these are the contents. So now we will start with the non-inverting amplifier. So this is a direct coupled non-inverting amplifier. So this is a circuit diagram of op-amp non-inverting amplifier circuit. Here the signal is applied to the non-inverting input terminal and the current output voltage gain is given by ACL equals R2 plus R3 divided by R3. Here VR3 will be equals to VI equals to I2 into R3 and I2 will be equals to V0 divided by R2 plus R3. ACL will be equals to V0 divided by VI, which will be equals to I2 into R2 plus R3 divided by I2 R3, and voltage gain ACL equals R2 plus R3 divided by R3, and where R1 will be equals to R2 parallel with R3. Here, in the non-inverting amplifier theory, circuit behaves similarly to a voltage follower circuit with one major difference. Instead of all the output voltage being fed directly back to the inverting input terminal, only a portion of V0 is fed back. The output voltage is divided by resistors R2 and R3, and the voltage across R3 is applied to the inverting input terminal. As in the case of voltage follower, the output voltage changes as necessary to keep the inverting input terminal voltage equal to that at the non-inverting input. Thus, the voltage VR3 always equals VI and the output voltage is then determined by the resistances of R2 and R3. Because the signal voltage is applied to the op-amp non-inverting input terminal, the output always has the same polarity as the input. A positive going input produces a positive going output and vice versa. Thus, the input is not inverted and the circuit is identified as a non-inverting amplifier. The voltage divider I2 is always selected to be very much larger than the operational amplifier input bias current, and VR3 will be equals to VI, which will be equals to I2 into R3, and I2 will be equals to V0 divided by R2 plus R3, and the circuit voltage gain it is given by ACL will be equals to V0 by VI, which will be equals to I2 into R2 plus R3 divided by I2 into R3, and also ACL will be equals to, if I2 and I2 cancels, then voltage gain ACL will be equals to R2 plus R3 divided by R3. So the above figure shows that a non-inverting amplifier theory with a resistor R1 connected in series with the non-inverting input terminal. As in the case of other op-amp circuits, this is done to equalize the resistor voltage drops produced by input bias current. In this case, R1 is selected to be approximately equal to the resistance seen looking out of the inverting input terminal. Thus, R1 will be equals to R2 parallel with R3. The input and output impedances for a non-inverting amplifier theory are easily determined from the negative feedback equations. Here the figure shows the non-inverting amplifier circuit with a resistor R1 in series with the input, where R1 is selected to be approximately equals to R2 parallel with the R3. Next, here it is a capacitor coupled non-inverting amplifier. In the last slide, we have explained the non-inverting amplifier. This is the capacitor coupled non-inverting amplifier. So, in this here, when a non-inverting amplifier is to have a signal capacitor coupled to its input. The op-amp non-inverting input terminal must be grounded via a resistor to provide a path for the input bias current. This is illustrated in the below figure where R1 allows for the passage of IB1. As in the case of the capacitor coupled voltage follower, the input resistance is essentially equals to R1 for the capacitor coupled non-inverting amplifier theory. Resistors R1, R2 and R3 in the capacitor coupled circuit are determined exactly as for a direct coupled non-inverting amplifier. So this is the circuit diagram of a non-inverting amplifier circuit with resistor R1 in series with the input resistor. input, and R1 is selected to be approximately equals to R2 parallel with R3. And this is the figure shows that a capacitor coupled non-inverting amplifier must have the non-inverting input terminal grounded via resistor to provide a path for the input bias current. Next, we will start the inverting amplifier. Here, this is a circuit diagram of an inverting amplifier. That is, op-amp inverting amplifier. That is, the signal voltage is applied via resistor R1 to the inverting input terminal. The circuit voltage gain is ACL will be equals to minus R2 by R1. And the current flowing through the resistor I1 will be equals to VR1 by R1, and VR1 will be equals to input voltage VI, and I1 will be equals to input voltage VI by R1. So, and also VR2 will be equals to I1 into R2, and output voltage V0 will be equals to minus I1 into R2. That is, in this direct coupled inverting amplifier, the circuit is termed an direct coupled inverting amplifier because with VI applied via R1 to the inverting input terminal, the output goes negative when the input goes positive and vice versa. Note that the non-inverting input terminal is grounded via resistor R3. With the non-inverting terminal grounded, the voltage at op-amp inverting input terminal remains closer to the ground. And any increase or decrease in the difference voltage between the two input terminals is amplified by the op-amp open loop gain and fed back via R2 and R1 to correct the change. Because the inverting input terminal is not grounded but remains close to ground, the inverting input terminal in this application is termed a virtual ground or virtual path. So current input, the circuit input current can be calculated as I1 equals VR1 by R1. The input voltage is applied to one end of R1 and the other end of R1 is at a ground level. Consequently, VR1 will be equals to VI, I1 will be equals to VI by R1. That is, I1 is always selected to be very much larger than the op-amp input bias current IB. Consequently, virtually all of I1 flows through resistor R2 and the voltage drop across R2 is given by the left side of R2 is connected to the op-amp inverting input terminal, which is always at a ground level. This means that the right side of R2 is VR2 below ground. So V0 will be equals to minus I1 into R2, where VR2 will be equals to I1 into R2. So the circuit voltage gain is given by ACL will be equals to V0 by Vi will be equals to minus I1 into R2 divided by I1 into R1. That is, voltage gain will be equals to minus R2 by R1. If the input of the inverting amplifier is grounded, then the circuit is seen to be exactly the same as a non-inverting amplifier with the R3 as the input resistor and 0 input voltage. Thus, negative feedback occurs to maintain the op-amp inverting input terminal at the same voltage level as the non-inverting input terminal. The input impedance of an inverting amplifier is easily determined by recalling that the right side of R1 is always at ground level and that the signal is applied to the left side of R1. Next, we have capacitor coupled inverting amplifier. So here the figure shows the capacitor coupled inverting amplifier circuit. Note that the flow of bias current is not interrupted by the capacitor C1. The capacitor coupled inverting amplifier circuit is shown in the figure. So here in this case, the bias current to the op-amp inverting input terminal flows that is from the output via the resistor R2 so that the input coupling capacitor does not interrupt the input bias current. And a voltage drop IBR2 is produced at the inverting input by the bias current flow. And this must be equalized by the IBR3 voltage drop at the non-inverting input. Therefore, for the capacitor coupled non-inverting circuit, R3 will be equals to R2. Apart from the selection of R3, the circuit is designed exactly as a direct coupled inverting amplifier, and the capacitor values are calculated in the same way as for the capacitor coupled non-inverting amplifier is calculated. Thank you.